Speak appropriately, that's right. If you were going to curse me out, today is not the day.
There's stuff over there.
Wait, why?
Great, thank you. All right, so I just want to make sure, first of all, that we are on the same page with regard to our electronic stuff. So at this point, all of you have become members of Edmodo, am I correct?
Yes.
Good. And have all of you become members of MMS?
No.
Okay. Well, today is your last day to do that, because what happens after this week, starting on Tuesday, is that your assignments will be on MMS only. Which means that if you're looking for them on Edmodo, you won't find them. Do what you need to do to get on MMS. Go to your guardian directly and tell him that you will not be able to do your work unless he does what he needs to do. Do what you need to do. All right? So you should be able to see a page that looks something like this. It won't look exactly like this because mine tells me whether or not I've graded it. Yours is going to tell me what kind of grade you've gotten on it, right?
I got 88. I don't know why.
Well, it's possible that you have not turned something in, or that, or it's possible that the little baby quizzes pulled you down. These quizzes will become much less important after we have our first real quiz, which will happen next week.
What are you doing?
Well, notice how many points these quizzes are worth. 2 and 4. The real quizzes are all worth 100.
Oh, okay.
So again, if you have not yet found MMS, make it so. To quote Captain Picard. Yes, ma'am. We are.
The other people, the seniors. Hi, seniors!
Okay. Now, our major goal for today is to talk about, continue to talk about exponential functions. I want to pick up where we left off, review really quickly, and then move into the lesson. Yep. Okay, everybody, give me the form of the exponential. F of x is equal to what? A b to the x. And a is called the
Initial value.
initial value. And b is called the base. And are there any restrictions on any of these quantities in here?
B cannot be less than 0.
True. Can b be 0? No. So b must be positive. What's the difference between not less than 0 and positive?
Well, positive is all positive numbers. 0 less than 0 can include 0.
Not less than 0.
Yeah.
That's right. So we have two different terms that you'll hear me use, and they're not synonyms, but they're really close. Non-negative means any number that's not negative, and positive, which means all numbers that are positive. The non-negatives include 0. Okay. Let's see here. And what about the domain of my exponential? What values am I allowed to plug in for x? all real numbers. The mean is negative infinity to infinity. What about the shape of the graph? It's going to be concave up, and it's going to be... Anything else? How else would you describe the shape? Concave up, I've got. Yes, that's what concave up means. Will it be increasing? Always? Sometimes. Under what condition? When b is greater than 1. Yeah. And what else can you tell me about the shape of the graph? I have... Does it go through the point 0, 1?
0, A.
0, A. That's right. It goes through here. It's going to be increasing concave up. Anything else I need to know? Good. And what kind of asymptote? Horizontal asymptote. So those are the 4 things about the graph that you should observe. This would be for a b greater than 1. What if my b is not greater than 1? What changes? Decreases? Still concave up? Does it still go through 0A? Does it still have a horizontal asymptote y equals 0? Yes. So the only thing that changes is the increasing and decreasing behavior for b's less than 1. Good. That's very good. What we did not talk about yesterday that I wanted to finish up are the properties of the exponential function that are really the properties of exponents. And these properties are expressed in terms of forms. And of course, you want to know these forms and be able to express them. And here they are. We're going to have 4 of them. 3 of them are for exponents with the same base. If I multiply a to the x times a to the y, I get a to the x plus y. Very good, x. And a to the x divided by a to the y. A to the x minus y. That was awful. And finally, if I raise a to the x to the y power, then that would be the same as a to the x times y. Is there any other way that I could write a to the x times y that would also be equivalent to it?
Would a x to y? No, it wouldn't be.
Oh, that's an interesting question. Is this the same as this? As it turns out, no, by convention. When I write this, it means that I first raise x to the y power and then raise a to that power. So a to the x to the y is not the same as that. But I can rewrite this in one other equivalent way. Who's got it? No, we just tried that. That was not effective. That's right. Because multiplication is commutative. That's right. And this is occasionally very, very useful. For example.
Oh, I know what you're going to do.
Okay. Let's see.
It's going to make that easy. And simple.
Let's do it like this. Suppose I have 4 to the 6 to the 1/2, and I wish to simplify this. Well, there's 3 different ways I could go about it, right? I can compute 4 to the 6. Do I really want to do that? No. Or I can multiply the exponents. And that's a little better. I could compute 4 to the 3rd. I guess I could do that. Or I could use this idea right here to say that this is the same as 4 to the 1/2 to the 6th power, and 4 to the 1/2 is 2 to the 6th, and 2 to the 6th might just happen to be a power of 2 that I've already learned, which is 64. Or if not, then I can do 4 to the 3rd. So it gives us flexibility in dealing with our exponents. Does that make sense? Okay. These are what I call the big three. They deal with the same base. What happens with the exponents? The fourth property deals with two different bases and the same exponent. And that is that if I have a to the x times b to the x, what do I get? What is that the same as?
A, B to the x.
Yeah, it's the same as the ab to the x. Now, it's possible to prove each of these properties for integers, but I can't prove them for all real numbers without making use of logarithms. If I were to prove them using integers, integer exponents, then it would look something like this. A to the x is a times a times a x times a to the y is a times a times a y times. So what I have is a times a x plus y times, and that's it. Similar kind of a thing here. This is a times a x times. And this is b times b x times. And if I just do a little bit of rearranging using commutative and associative properties, I can write this as a times b times a times b times a times b, and I will have exactly x factors of a times b. Sometimes visualizing these helps you to see these properties. Does that make sense? Good. Cool. I'm glad we made some sense today. Now, here is the tragic reality. Students will try to make up their own exponent properties just because. This is never, well, it's never helpful unless you can prove it. If you want to make up your own exponent properties and you can prove them, I'll take it. But if you want to make them up and just because it looks good, we don't do math like that. These four exponent properties here are going to be the ones that you want to use. Let me consider one that students will often try to do. What will they often try to do? Yeah, they'll just, because what they have in mind is that we're talking about some kind of distributive property, and we're not. There is no distributive property of exponents over addition. And here's one place where it really shows up. I'll get students who will try this nonsense. They'll look at that and say, aha, the square root of x squared plus 4, that must be x plus 2. No, 1,000 times no. Because exponents do not distribute over addition. Why not? Well, because exponents mean multiplying by itself, right? So if you want a counterexample to help keep your head straight, to help you remember that exponents do not distribute over addition, then remember the really simple one. A plus b squared is by no means a squared plus b squared, but it is instead a plus b times a plus b, which is a squared plus 2ab plus b squared. See? And if you remember that simple counterexample, then you will never be tempted to try to distribute your exponents over addition. Well, this raises an important question that I am not going to answer at this time, but I will answer later, which is, can we do anything to simplify a plus b to the x power? And the answer turns out to be yes, if x is a positive integer. And we'll get there far in the future. okay? Using the binomial theorem. But I'll give you a hint. If x is a positive integer, then what we're doing is multiplying out a plus b times itself x number of times. And that suggests that I should end up with something that involves powers of a and involves powers of b. Okay? Questions, comments, or jokes? All right. Then let's talk about the inverse function of exponentials, which are the logarithms. The log base a of x is the inverse of y equals a to the x. And what does it mean to be an inverse function? Well, we use that as a procedure to find inverses, but what does it mean to be an inverse?
It means the input of one is the output of the other.
Input of one is the output of the other, which is another way of saying switch the y and the x. Here's how we're going to define inverses in mathematical terms so that we can use them computationally. This is what it means to be an inverse. That f of f inverse is equal to x, and f inverse of f is also equal to x. In other words, the function and its inverse clobber each other and give you x back. So for example, f of x equals 3x, and f of x equals x over 3 are inverses. Why? Because 3x over 3 is x. The functions cancel. For positive x, f of x equals x squared, and g of x equals root x are inverses. Because the square root of x squared is equal to x for positive x's, and the square root of x quantity squared is also equal to x for positive x's. Notice this is not true for negative x's. If I take negative 3 and square it, I get, if I take negative 3 and square it, I get 9, and the square root of 9 is 3, which is not equal to negative 3. So f of x equals x squared is not invertible on its entire domain, but only for positive, really non-negative x's. Well, so when I say that the log a of x is the inverse of y equals a to the x, what I mean is that the defining property of logs is that they cancel exponentials to give you the exponent. That the log a base a of a to the x is x. And for this reason, we have a slogan, and that is that the log is the exponent. This is what that slogan means in math terms. And likewise, when I raise a to the log base a x power, I get x. Now let me do a couple of illustrations, examples, and you'll see why I say that the log is the exponent. Suppose I want log base 3 of 27. If I take a moment to write 27 as a power of 3, 27 is 3 to the third power, then the log and the exponent cancel each other, giving me the exponent here. Likewise, log base 3 of 81. 81 is 3 to the fourth power. log and the exponent cancel, giving you the exponent. So the log is the now, here we had nice, convenient, easy properties, kind of like special angles and trig, right? What if I wanted the log base 3 of, oh, I don't know, 36, something like that? Then that is going to be some decimal value that is between 3 and 4. It will be an irrational number. So the log is a continuous function. What if I wanted the log base 2? How about the log base 4 of 2? Can I write 2 as a power of 4? 2 is 4 to the... Yeah, that's right. So the log and the exponent, the exponential cancel, giving me the power. Just like that. So what do you need to be able to do with logs? Well, first of all, you should be able to do some computations. So if I give you fairly simple stuff, you should be able to compute. In particular, this is where logs show up a lot of times in chemistry. What would the log base 10 of 0.01 be? Everybody write that down. Log base 10 of 0.01. What is that? Got an answer? Got an answer? You got one? So 0.01 is 10 to what power? Not negative 1, negative 2. Yeah. And so that log is negative 2. Scientific notation, all that good stuff. So why do we use logs? The main use of logs, well, I should say, it's going to turn out as time goes on in this class that logs are going to be our best friends, because logs give us a way to turn exponent problems into multiplication problems, and a way to turn multiplication problems into addition problems. Historically, that's why logs were created. But the major use, the first primary use of logs is to solve exponentials. So, for example, I wish to know, let's make this slightly harder. I wish to know all the values of x that make this equation true. Well, I can do a little bit by dividing both sides by 4, right? And that gets me this far. But now I need to do something to find that exponent x. Wait a second, the log is the exponent. And therefore, I can apply log base 2 to both sides of this equation. Canceling my x and giving me a solution, just like that. This is a legitimate number, so I don't need to simplify this any further. If I need a decimal approximation, then my calculator might be able to give it to me, but I might need a special property of logs to get it. Okay? How are we doing so far? Did you do logs last year?
Yes.
Did they make sense?
Yes.
They did. Okay, good. So we're covering. Does this make sense now? Good, good. All right. So we might ask, what are the properties that log x has? The properties of log base a of x are going to imitate the properties of a to the x because those two functions are inverses. So let's write the properties of the exponential over here, and that is that when you multiply the product a to the x times a to the y, you get a to the x plus y. In inverse fashion, when I take log base a of x times y, the log of the product, I get the sum of the logs. The log of the product is the sum of the logs. In other words, exponents add because the log is the exponent. When we divide, we subtract exponents. Therefore, the log of a quotient is the difference of the logs. The exponents subtracted. Likewise, power to a power gives you a to the product of exponents. Hence, the log of a power is power times log. The exponents multiply. And that's it. Now, these properties are not difficult if you remember the forms. If you take some time over your long weekend to simply write out these forms so that you know them, you're good. Where students run into trouble is twofold. First of all, they, instead of learning these forms, they try to turn them into rules. Well, when you see this, you add. That's horrible. That's not math. That's like trained monkey stuff. And the reason that it's horrible is that you're never really sure if those rules that you make for yourself apply in this situation. You know what I'm saying? Whereas if you know the form, then you can say, oh look, this fits the form, and I can do that because that's the form. And you never have to guess. So learn the forms. Do not try to turn them into rules for yourself, like do this. Learn those forms. The second thing that students will do, is that instead of following the forms, they will try to do it by intuition. So I get a whole lot of this kind of a thing. No, wrong. Not. Why did that happen? Because the student looked at it and said, it feels right. Math is not done by feeling. We do have feelings in math. We do experience emotion. We experience the relief of finally figuring out how to do a problem. We experience the joy of seeing a clever solution. We experience the intrigue of an interesting idea. But we do not solve problems by feeling our way through. We do it by cold, calculated reasoning. And we use forms to generate that reasoning. What is the right way to simplify this using our forms? What should this be? Well, yes, I could go towards simplifying the inside here, but if I wish to simplify this using log properties, yeah, that's it. The log of a product is the sum of logs, which is my slogan for my form. Does that make sense to everybody here? And likewise, just like you can't make up your own exponential rules unless you prove them, You also cannot make up your own log rules unless you prove them. And in particular, I'll have a lot of students that will look at this and they will say, oh look, that's log x minus log 1. No, it's not. There is no log property for sums and differences. And there's an interesting thing about that. If there were a log property for sums and differences, breaking secret codes, the secret codes that we currently have, would be an easy matter, and all of our secret information would be blown instantly. If somebody could come up with a formula for the log of a difference or the log of a sum. Well, I promised you 4 log properties, and we only see 3 here. And that's because we have 3 properties that involve a single base log a. I'd like to come up with a 4th property that will be our change of base property. And I'll actually provide a proof for it, but you may not have seen it before. Here's the difficulty that I have. I have log base a of x, but for whatever reason, I need to convert it into a different base. I need to find log base b of x. And so the question is there a mathematical relationship between these two that will let me convert one into the other so that I can compute them? And there might be some practical reasons for doing that. I'll just give you an example. Suppose I asked you, what is the log base square root of 3 of 9? And you look at that and you go, huh, that's a weird problem. Maybe it's 6. We'll see if she's right in just a minute. Okay? So what I would love to do is to be able to convert this into a log base 3 somehow. Oh, now she thinks it's 4. Wow. So I'd love to be able to convert this into a log base 3, right? Because I could deal with log base 3. So how do I do that? All right. What I'm going to claim is this, that the log base b of x is the same as the log base a of x divided by the log of the new base. That the factor 1 over log base a of b is a conversion factor that lets me convert logs from one base to another. And I'm going to prove this by showing that both of these must be equal to one another. So let's begin by letting y equal a to the x. And what I would like to do is I would like to solve for x by 2 different methods. First of all, I'd like to solve for x directly by taking the log base a of both sides. Now on the left-hand side, I simply have log base a of y, and that is what it is. On the right-hand side, the log and the exponential are inverse functions, and they cancel, giving me the exponent x. The log is my exponent. And so that's good. But also, I'd like to take that equation and give it color. That same equation, and I would like to solve for x by applying log base b to both sides. I'm certainly allowed to do that. It's a little exotic. But the reason that I'm motivated to do that is that I'm looking for log base b of x. And so I'm hoping that something will work out. This gives me log base b of y. Maybe that's good. And so on the right-hand side, I'm going to use the exponent property of logs. Log base b of a to the x is the same as power times the log. Here's the big move. This was the important move here. And if I now divide both sides by log base b of a, then I discover that x is equal to log base by divided by log base b of a. Wait a second. I solved for x, and I solved for x again, and I got two different expressions. What must be true?
They say y equals fraction.
Because they are both equal to x. Good old transitive property of equality, going all the way back to geometry. So I conclude and so we have this. Now, how does that relate to my original thing? Well, the a and the b are arbitrary, right? And the symbol y here is also arbitrary. So I could just as easily write this property as log base b of x is equal to log base a of x over log base a of b, swapping the roles of a and b in my formula. And so this is called the change of base form. And in particular, I have a special case if x is exactly equal to a, then I get this very, very interesting result. The log base a of a must be 1, right? Because that's a to the first power. And I find that the log base b of a is the reciprocal of the log base a of b. Very, very interesting.
What did you just erase?
Oh. It has not gone. So I want to come back to Delina's puzzle and use the change of base property to get a definitive answer here. Log base root 3 of 9. What an exotic problem. But I'm going to rewrite that using a new base. I'm going to rewrite that as the log base 3 of 9 divided by the log base 3 of root 3. Aha! And the log base 3 of 9 is easy. What value is that? 2. And the log base 3 of root 3 is also easy. It is 0.5 or 1/2. And division is multiplying by the reciprocal. So I get 4. Sue, you look like you have a question. What is your question? Here. Think of this as 3 to a power. 3 to what power? No. 3 to the negative 1 would be 1 over 3. Okay, good. So let's clear this up, because students are sometimes confused. This is not a log thing. This is an exponent thing. A to the 1/2 power is the square root of a. Why? Because if I square it, I get a. Right? A to the negative 1 power is 1 over a. Why? Because if I multiply a times a to the negative 1, I get a to the first times a to the negative 1, which is a to the 0, which is equal to 1. And therefore a to the minus 1 is equal to literally 1 over a. In fact, the way that cool mathematicians write division, A divided by B, is to write it as A times the reciprocal of B. B reciprocal. This is the way that cool mathematicians think about division. So division is multiplying by the reciprocal. Does that clear that up? Good. So let's practice both with this idea and our logs. What's log base 5 of 125? 3. That's right. Because 125 is 5 to the third. What's log base 5 of 0.2? -1, that's right, because 0.2 is 1/5, or 5 to the -1. What is log base 5 of 5√5? 2 ways to do this. Give us one way to do it.
So you turn that into log base 5 of 5 plus log base 5 of root 5.
Love it. Log properties to the rescue. Always and forever. Those log properties are lifesavers, so the sooner that you learn them, the sooner you'll start seeing opportunities to use them. Keep going.
Log base 5 of 5 is 1, log base 5 of root 5 is 1/2. The answer is 1.
Yes. And this suggests a way that I could have done it differently. I could have written 5 times root 5 as 5 times 5 to the 1/2, or 5 to the 3/2 power. Cancel and get 3/2. So with these logarithm problems, there very often is going to be a couple of alternate pathways to get there. Does that make sense to everybody? Good. Did you do log properties last year? Somewhat? A little bit. Does this make sense?
Good. Last year we just used base 10 for everything.
Okay. We, this year, interestingly, are going to use base E for a whole lot of stuff. Okay? E doesn't look very natural to you. And you may wonder, why is it called the natural base? In fact, the exponential e to the x has an inverse of ln, or natural log. When the time comes, I will explain to you how it is that the number e comes about very naturally as the solution to certain types of differential equations. Okay? But for now, don't worry too much about ln's, other than to observe that there is an ln button on your calculator, and so it must be important. Natural log.
Just read LN.
How do you read it? Natural log.
Log.
Just read the log.
Log.
Oh,
Log.